This is a blue jay feather. That shouldn't happen. Destroying an object's shape is not supposed to destroy its color. Unless the color was never a pigment in the first place. Fruit, flowers, feathers, fish, fur. The living world is soaked in color. Berries run red. Flowers run yellow and orange. Leaves run green, then gold, then brown. Fur runs through every shade of grey and black and tan you can name, and most of it is made the same way, with pigment. Now ask for blue. The list gets short very quickly. True blue pigment is essentially absent from mammalian fur. No blue dogs, no blue horses, no blue cats. Across animals generally it is rare, and rare in a way that red and yellow and brown simply are not. And yet blue is not hard to find. A jay, a kingfisher, a morpho butterfly, a peacock. So one of two things has to be true. Either nature almost never manages blue, or a lot of the blue you can see is being made some other way. Start with how color usually works. White light is every wavelength at once. When it lands on something, pigment molecules absorb some of those wavelengths and the rest comes back. What comes back is what you see. A cardinal is red because of carotenoids, pigment molecules sitting in the feather, soaking up almost everything except red. Grind that feather to dust and the molecules are still there, still absorbing, still red. You can destroy the feather completely and the color does not care. That is the deal a pigment makes. It is a molecule shaped to swallow particular wavelengths, and the color you see is whatever it failed to swallow. Which is what color is supposed to do. It belongs to the material, and it survives the material being taken apart. Which is exactly what makes the other feather a problem. So go in. A feather is a shaft with rows of barbs coming off it. Each barb carries smaller branches called barbules. Closer still, and a single barbule is a rod of keratin, the same protein as your fingernails. Keratin is not blue. Nothing down here is blue. But inside that rod is a sponge. Keratin threaded through with pockets of air, and those pockets are spaced at a particular size. Not in a perfect lattice, but close enough and consistently enough that it matters. Because the spacing is about the width of a wavelength of light. White light goes in and scatters off boundary after boundary between keratin and air. Waves that come back in step with each other reinforce. Waves that come back out of step cancel. The spacing decides which is which. At this spacing, most of the spectrum cancels itself out, and blue reinforces. Blue is the wavelength that survives the trip. The feather is not blue. The feather is built in a way that sends blue back to you. Nothing has been added. Nothing in there is colored. A shape is doing the job a pigment usually does. And now the first 30 seconds make sense. Crushing it did not remove a pigment. There was no pigment. It destroyed a spacing, and a spacing does not survive being crushed. Once you know what to look for, it is everywhere. A morpho butterfly's wing has no blue pigment either. Its scales are built in ridged layers that do the same job by different means. Watch one turn. The blue flares, shifts, drops away, comes back. Because at every new angle the light meets those layers differently. Now turn the jay feather. It barely changes. The morpho's layers are stacked in near-perfect register, so where you stand decides what survives the trip out. The jay's pockets are scattered. ordered enough to pick blue out of white light, disordered enough that it hardly matters where you stand to look at it. One announces its structure every time it moves, the other hides it. Same color, two completely different pieces of engineering. None of this means blue pigment is impossible. There is a butterfly called Nesea that carries a real one. Crush its wing and the blue holds. The molecules are still there. And a hydrangea takes a third route. The pigment in its petals is the same molecule whether the flower comes out pink or blue. What changes is the soil and how much aluminium the plant can pull out of it. The aluminium binds to the pigment and the color moves. And then there are the two largest blue things you will ever see. The sky is not blue. There is nothing blue in the air. Sunlight hits the molecules of the atmosphere, and the shorter wavelengths scatter far more strongly than the long ones. So blue arrives at your eye from every direction at once. The ocean is not doing that at all. Water absorbs light, and it takes the long wavelengths first. Red is gone within a few meters. Orange, then yellow, then green follow it down. What is left to come back up is blue. Two of the largest surfaces on the planet, and they are not blue for the same reason as each other, or as the feather, or as the butterfly, or as the flower. Blue is not an ingredient, it is a result, and nature gets there by whatever route is available. Go back to the feather. Change the light in the room and its color changes with it. Turn the morpho and its color changes. Turn the lights off completely and the blue is not dim, it is gone. Nothing about the feather has moved, because the blue was never sitting inside it, waiting. At the far end of all of this is you. Three kinds of cone cell, tuned to overlapping bands of a spectrum that runs enormously wider than anything you can see. Your eye samples a sliver of it, and your brain returns a verdict. Not a measurement, a verdict, assembled from three overlapping signals and handed to you as though it were a fact about the object. Every mechanism in this film, the sponge, the ridges, the pigment, the aluminium, the atmosphere, the water, is completely different from all the others. And every one of them ends in the same place. Blue was not waiting inside the feather. It happened when light met a structure, and then met you.